All right, guys. So let's do a quick recap from yesterday. We went over finding valence electrons, drawing dot structures for atoms, ions, and ionic compounds. So here we're going to draw the dot structures for barium, the barium ion, chlorine, the chloride ion, and magnesium nitride. So looking at this barium that is given does not have a charge. So remember, we need to find its location on the periodic table. It is in the second column, meaning that it has two valence electrons. It's in that group 2A. So remember, we're going to draw the two valence electrons around the atom, but remember, we cannot pair them yet until there are at least four around that atom. For the barium ion, which it tells you is a +2 charge, and remember the charge can be found kind of by the column as well. That means that since it's a +2, it means it lost 2 electrons. So this is our dot structure where it is empty and has lost those 2 valence electrons. For chlorine, it is number 17 on the periodic table. It's in that group 7A. So it has 7 valence electrons that will be drawn around the atom. For the chloride ion, remember the negative charge means that it gains an electron. These want to be full and have that full octet. So this will have all 8 electrons around it. And you may see it with or without brackets. Last one is the magnesium nitride, the Mg3N2. Remember that means that we have 3 magnesiums and 2 nitrogens. Magnesium is in the second column on the periodic table, so it has 2 valence electrons on each of these. Nitrogen is in group 5A, so each of these has 5 valence electrons. So remember, this has a metal and a nonmetal, so it is an ionic compound. Ionic compounds we represent showing that transfer of electrons. So remember, all the metals are trying to become empty, where that inner layer of valence electrons is full, whereas the nitrogens, the nonmetals, are trying to get that full octet to be full with 8. So magnesium will give 2 electrons to that first nitrogen. Magnesium is now empty, but nitrogen only has 7 electrons now, so it needs 1 more. So it'll take 1 from the second magnesium. Now that nitrogen is full, but magnesium still has 1 electron to get rid of. So that's where a second nitrogen comes in. It'll give that extra electron to nitrogen. So now that second magnesium is empty, but now that second nitrogen only has 6 electrons, which is where a third magnesium comes in to give up its 2 electrons. So now all 3 magnesiums are empty and both nitrogens are full with 8. So remember, this showing the arrows and the electron transfer is the complete dot structure for magnesium nitride. All right, guys, let's switch over to our notes, and today we're going to focus on those molecular covalent compounds. So with molecular compounds, they are going to be held together with a covalent bond. A covalent bond is an attraction between atoms that are sharing electrons. So whereas ionic had a transfer of electrons, covalent is going to be sharing those electrons to where they belong to both atoms that are attached. These are going to make up a molecule. A molecule is an electrically neutral group of atoms that are held together with those covalent bonds. So by sharing electrons, we do have some substances that are considered diatomic molecules. These are molecules that are made up of two atoms. So di means two. These are things that do not exist in nature as a single atom. They are never found by themselves. They always have to have a partner. The diatomic molecules you do need to be aware of, and you'll see these. There are a couple ways to remember them. One way is the anagram Brinkelhoff. So Brinkelhoff, the 7 diatomic molecules are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. All of those are never found by themselves in nature. So like oxygen that we breathe is O2, because you're never going to have an oxygen floating around by itself. Another way to remember these is there are 7 of them. They're the dynamic 7. On the periodic table, if you start at number 7 on the periodic table, nitrogen, and actually draw a 7 with your finger, that goes through nitrogen, oxygen, fluorine, chlorine, bromine, and I didn't leave myself enough space, iodine. That is 6 of the 7. And don't forget, hydrogen is kind of off by itself. So those are 2 ways to remember the 7 diatomic molecules. And we're going to be using those several times throughout this unit. A molecular compound is a compound composed of molecules, so it's composed of only nonmetals. So remember, ionic was a metal and a nonmetal. Molecular compounds are only nonmetals. And molecular compounds, sorry guys, molecular compounds tend to have low melting points and boiling points, whereas ionic and metallics have high. All right, so like I said, ionic compounds had the high melting points and boiling points. They tended to be solids at room temperature, whereas molecular compounds have lower melting points and boiling points. So majority of these are actually gases at room temperature, with a few exceptions that are liquid. So looking at properties of our covalent compounds or molecular compounds, like I said, they have low melting points and boiling points. They have very poor electrical conductivity. They actually tend to not conduct electricity in general or heat. So these tend to be used as like insulation in houses and things like that. And molecular compounds tend to have a polar nature. We're going to talk about that more at the end of the unit. But it just means that even though electrons are being shared, they may not be shared equally. So with molecular compounds, they are written out with those molecular chemical formulas. So the chemical formula shows the kinds and number of atoms present in a molecule of a compound. So the formula tells you which elements are involved and how many atoms of each element you have. So for example, water, everyone knows water is H2O. That means it has 2 hydrogens and 1 oxygen always. So this tells you how many of each atom you have, but it doesn't tell you how they bond together. It doesn't tell you, do the 2 hydrogens attach to each other, or do the 2 hydrogens attach to the oxygen? So that's where we use diagrams or dot structures to look at the arrangement of atoms, to look at how these bond together. So with covalent bonding, when forming covalent bonds, electron sharing occurs so that atoms with the shared electrons included have that full octet. So remember, everything is trying to have 8 total valence electrons, which is the same as a noble gas. The exception is hydrogen. Helium, remember, can only have up to 2 total electrons. So everything is trying to have 8, with the exception of hydrogen when we're bonding. And in a compound, atoms will share electrons until every atom has a complete octet. So the electrons do not have to stay on their original atom. So like we said, covalent compounds, they will share enough for everything to have 8, whereas ionic, they transferred enough electrons for everything to have 8. Excuse me, I hit an extra button. So first thing that's going to form is a single covalent bond. This is the most common one we come across. This is where 2 atoms are going to be held together by sharing a single pair of electrons. Is going to be considered a single covalent bond. This is how a lot of our diatomic molecules are held together. So diatomic molecules are all sharing electrons. The diatomic molecules that are single covalently bonded together are hydrogen and are halogens. So remember, that's that group 7A. And any electrons that we have that are not shared by the atoms are referred to as unshared pairs of electrons. So those will be represented as dots. So just to show you what this looks like, kind of simplified. So remember, hydrogen is H2. Hydrogen has 1 valence electron. They simply share their 1 valence electrons that they both have access to 2. With our halogens, I'll pick fluorine because that's the one that's at the top. So fluorine is F2. Each fluorine has 7 valence electrons. So what they'll do is they will share that 1. That way they both have 8 whenever you're including that bond. So anytime you see a bond, that is representing 2 electrons. And like you can see on fluorine, those dots around the fluorine, those are those unshared pairs of electrons we were referring to. So the single covalent bond filled the octet for those particular molecules. Well, if sharing 1 pair of electrons doesn't fill the octet, we can also form double and triple bonds. So atoms will form double or triple bonds if they cannot attain a full octet by sharing only 1 pair of electrons. So they will continue sharing until the atoms are full. In a double bond, this forms between atoms that share 2 pairs of electrons. So that will have a bond with 2 lines, which remember each line was 2 electrons. This will represent 4 electrons. A diatomic that's held together by a double bond is oxygen. So oxygen has 6 valence electrons. So whenever it shares 1 pair of electrons, that's only 7 valence electrons. So it would need to have a second pair shared. So you'll see this kind of cleaned up where you have that double bond in the middle. If they still do not have a full octet, a triple bond can form. So triple bonds will form between atoms that share 3 pairs of electrons. So each bond is 2 electrons, so we'll share a total of 6 electrons. This, if we look at nitrogen, each nitrogen has 5 valence electrons. If they share 1, they only have access to 6. When they share a second pair, they both only have access to 7. So they have to share a third pair. And I'll clean that up a little bit. So they will share a third pair of electrons. That way both nitrogens have access to 8. So all of our diatomic molecules are held together with covalent bonds. Like we said, hydrogen, the halogens are single bonded. Oxygen has to be double bonded. Nitrogen has to be triple bonded. And the atoms become closer together with an increased number of bonds holding them together. So single bonds are rather long in comparison to the other ones. When a double bond is formed, it cuts that space in half essentially, and the atoms are now closer together. When there's a triple bond, it pulls those atoms even closer together. And in general, the more bonds there are, the stronger they are. So it's the higher the energy is needed to break those bonds. So as you increase the number of bonds, the length of the bond gets shorter, but it also gets stronger. It's going to be harder to break when there are multiple bonds there. Guys, so just to summarize, a single bond we said is sharing 2 electrons. This is always the first one that forms. It is the longest and therefore the weakest. A double bond can form next if needed. That shares a total of 4 electrons, and it gets a little bit stronger, but also a little bit shorter. Whereas a triple bond is the shortest of the 3. That's sharing a total of 6 electrons, and it is the strongest. I'm gonna have to stop here to take care of the baby, and I will record a part 2 going over drawing these dot structures. Molecular dot structures are the more common ones we tend to draw, so make sure to check back for part 2.